we had just calculated our z-score using this crazy formula, and we ended up with 0.36 as our z-score. When we did the first example, we were doing a t-test. This one ended up being a z-test, and so I'm using my z-table, and I'm going to go find 0.36 on my z-table. So my z-table is the one where I'm using the one I like, the one Beitner's using, not the one Lang's using, but they both will give you the same value ultimately. 0.36 on this one, 0.3 is here, the 6 is here. So 0.6406 is the number that I'm getting from the table. So when I had posted these solutions online, I said, when z is 0.36, the probability from our table is 0.6406. The table that I'm using gives us the value all the way under the curve up to that z-score, but I actually want the value under the tail. So I want the opposite of that amount. So I want z1 minus that 0.6406, which comes out to be 0.3594. Okay. One slightly extra complication is that this is also a two-tail test. And so this right here, the 0.3594, gives me just one tail, and I need the other tail, which I know feels like it's confusing because you're like, but it's all filled in over here, and go, yeah, this is different when we're talking about the probability part. This part of the graph is the probability on the tail, and I want to multiply it by 2 because it's a two-tail test. So I'm taking that 0.3594 and multiplying it by 2 to get our p-value. So the p-value comes out to be 0.7188. When we're doing a p-value check, you're comparing the p-value to whatever the alpha level was for this particular problem, and they gave us an alpha of 0.05. So what we want is for the p-value to be way smaller than that 0.05, but the p-value is actually bigger than that. So that means we have to fail to reject the null hypothesis. So if we get a p-value that's bigger than our alpha level, then we can't reject the null hypothesis. So we can't really say anything interesting about this data. So when it says what conclusion can be drawn from the study, because I had to fail to reject the null hypothesis, it means the null hypothesis is the one that we're going to hold to. It doesn't mean the null hypothesis is necessarily true, but it means I don't have enough evidence to reject it. So there's no significant difference between the proportion of headache sufferers taking the Nasonex versus the placebo group. So because this ended up being the boring case, I say there's no difference between the two groups. That was my null hypothesis. So I had posted all this online, but I know the week probably got crazy and not everyone got to check back in on that. So I wanted to go over that last part before I jump into the other things. I'm gonna pass out a new handout. I got a request last night to go over that problem that is on the first page. And then the problem that's on the back page is a matched sampled t-test. That direction. Okay. Well, I made a handout again so we don't have to write all the words down because these problems all have a lot of words. And it's not exactly the homework question, it's the thing that pops up when you miss the homework question. So I'm explaining how that works. You'll have to make a slight adjustment for the homework question, but so will everyone because usually different numbers pop up for everyone. In planning for a new forest road to be used for tree harvesting, planners must select the location that will minimize tractor skidding distance. Researchers wanted to estimate the true mean skidding distance along a new road in a European forest. the skidding distance in meters were measured at randomly selected road sites. A sample of 16 of these values is given in the accompanying table, and we want to use that information to find the 95% confidence interval to estimate the population mean skidding distance. So these are our 16 values. We're going to go find the mean of all those values. And then to find the confidence interval, we have that formula where I'm not just going to take the mean, I also need the t-score for a 95% confidence interval. And we're going to multiply that by the standard deviation for the sample divided by the square root of the sample size. So we have a formula for that. After I do that, I'm going to give a practical interpretation of the interval. What that means is, like, in real words, what the heck just happened? What does it mean? Then it asks what conditions are required for the inference to be valid, and are these conditions satisfied? So I'll talk through what that means. And then the very last part says, a logger working on the road claims the mean skidding distance is at least 450 meters. Do you agree? So we can't say anything until we have our confidence interval, but once we have it, then we'll be able to say something. Okay. So the email that I got was, I have no idea how to do this, Jen. That's okay. So from the get-go, here's the first thing. They're talking about a confidence interval for the mean skidding distance. So I obviously need the mean of all of those numbers. There's 16 of them. So I need to add up all those numbers and I need to divide by 16. If you trust me, I will tell you what that number is. You don't necessarily need to add up all those numbers. I will tell you the sample mean. I took all 16 of those numbers, I added them up and I divided by 16 and I got 373.75 when I did that. It's good to be able to do that, but at this point in time, you being able to calculate a mean is a thing we assume you know how to do. So me giving you a mean doesn't feel like cheating, because I'm like, if I gave you enough money, if I handed you a $20 bill and I said, could you find the mean of 100 numbers? You'd go, yeah, I don't want to, but I will. And you'll just take those 100 numbers, add them all up and divide by 100. It's not hard, it's just annoying, right? So we would have to take all of those numbers, add them up and divide by 16. And that will give us that number right there, okay? I also know that the formula for my confidence interval looks like this. I'm going to take that sample mean I just got, and then it's plus or minus. This I know is going to be a t value. Why do I know it's going to be a t value? Why am I saying t instead of z here? Small sample size. There were only 16 scores here. It's not 30 or more. So I really have no choice. It's going to have to be a T here for both classes. Regardless, you'd all be on the T table. Okay. So it's a T alpha over 2 if I just want to say the mean skidding distance is more than or less than some particular amount. So I'm going to do a two-tailed test. We're doing a confidence interval on it first. So all I'm going to do is take that t score there and we're going to multiply it by the standard deviation for the sample, which we call S. And then we divide that by the square root of our sample size, or the square root of n here. That's your formula for a confidence interval. So I've got the x bar part. The t alpha over 2 is not so hard to find. I just needed to know that what they're asking me for is a 95% confidence interval. Then my t alpha over 2 for a 95% confidence interval means I'm going to my t table, and 95%, and it's a two-tailed test, means that there's 2.5% in each of the tails, because it's 5% overall between the two tails. And so that means you're going to the 0.975 number, because if it was 95 and you added 2.5 to that, you'd get 97.5. So what I'm looking for is the 0.975. What is the degrees of freedom for this one? $15. How'd you do that? So the n was 16 on this one. Degrees of freedom is just going to be n minus 1. So we're looking for degrees of freedom 15 on this thing. And in terms of my table, I'm looking in the column that's 0.975. So 0.975, and I'm coming down to 15. And so the number that I'm going to get here is 2.131. 0.975, again, you're using that column because it's a 95% confidence interval and it's a two-tail test. 95% confidence interval means there's 5% in the tails. And since it's a two-tail test, that means you're cutting that number in half. So you're putting 2.5% in each of the tails. So you have to put 95 plus 2.5 more, that gets you to the 97.5. So that's why we're in that column. 2.131 is our T. Okay. How are you doing so far? Any of the things I've said, you're like, what?
I think we have a different table that we do.
You guys have a different T table?
I think so. It's like ours goes by like, say if we were talking like the T alpha over T, it would be like 0.0025.
Cool.
Like T.
So yours will be 1 minus whatever mine says. Cool. So each class might have a different table. Dang it, sorry. So for you guys, you would be looking for the 0.025 column. Yeah. All right. So the only thing I don't have in this formula now, I have the X bar, that's right there. I have the T alpha over 2, that's right there. I already know what the N is, that's 16. I don't know the X. That's the standard deviation. Now, bad news is if they really truly don't give you the standard deviation when you go to do this problem, they want you to calculate it. Good news might be your calculator could do it for you depending on which calculator you have. It's possible your calculator can't do it for you if you don't have a particularly nice calculator. So there's different realities of what could set in. If you actually need to go do this calculation, here's a reminder on what that formula is. Your standard deviation is equal to the square root of, and you would take the sum of each of those X values. So this 488, the 350, the 457, all of those are your X values. We call those the X sub i's. You would take each of those X values and you would subtract the X bar from them and square it and divide that by n minus 1. That's the formula for calculating the standard deviation. For a sample of 16 of those, I doubt that's actually what they really want you to do. For a homework problem, it is very easy for you to pull up another screen, and literally on your other screen, what you can do is you can type in mean and standard deviation calculator. See how it even filled it in? I didn't even finish typing those words. There's lots of them that you can pick. If that's what you're going to do, what you do is you type in the list of numbers up there and it will calculate those things for you. So you don't necessarily need to do that for homework problems. If it's a test and they haven't given it to you, you'll want to have that dang formula on there, but they're probably not going to give you 16 of them to do because that will take a while, right? So if you trust me, I will also give you this number because Jen already did it for you. Your number is 116.581,588. You probably don't need that many decimal places, but I just wrote that many down. Typically, what they're going to want you to do, they'll sometimes give you all those numbers and then they'll say, go calculate that confidence interval. So I'm ready to calculate it. X bar plus or minus my T sub alpha over 2 times the standard deviation for the sample divided by the square root of n. I have all of those things now. So 373.75 plus or minus the 2.131. We're going to multiply that by the 116.581588 divided by the square root. And my sample size was 16. So that's what you're plugging in. And so one of the times we're going to do 373.75 plus 2.13 times this. And one of the times you're going to do 373.75 minus the 2.131 times that thing. That's how you get your confidence interval. So your confidence interval is going to be two numbers separated by a comma. So I'll do the smaller one first. So that's me doing the minus 373.75 minus 2.131 times 116.581588 divided by the square root of 16 is just 4. All right, so I got 311.6 if I round it as my lower number. And I'm going to do it again, but I'm going to do it with a plus now. So 373.75 plus 2.131 times 116.581588 divided by my square root of 16 is just 4. And I got 435.9 if I round it. It mattered that this was a 95% confidence interval. That's why I used the 2.131. If your homework problem told you to do a 90% confidence interval, then you're going to have a different T value in there. But everything else in there is going to be the same. So the size of the confidence interval will be changed by whatever if it's 90%, 95%, 98%, you got to check. Question.
Sorry. For the T value, I know that you have to do degrees of freedom, which is like 15, but then like on this side, what do you look for? Sorry.
Yeah. So my degrees of freedom were this way. Depending on which class you're in, what we were looking for, we wanted a 95% confidence interval. So 95% confidence interval means that you have left 2.5% in this tail, and you've left 2.5% over in this tail, and that there's 95% between these two right here. Okay, so when we go to figure out what value we want, the way the T table is working is it's looking for whatever the number is over here. And if we end up wanting the negative of that number, it'll be the same amount under here. We would just, if so, like if you were looking for our T value was yeah, so if we wanted a negative 2.131, it'll be the same like procedure. It'll go through the same thing. So in what we're doing then, if I want 2.5% to be over here, then on this table, the way it's marked at the top, it has 0.9, 0.95, 0.975, 0.99. Then I have to take the 95% and I have to add 2.5 to it. And I get 97.5, which is why I'm in this column. So I went to degrees of freedom 15 and I came over to that third column, and that's where I got the 2.131. However, we also heard that some of the tables don't have these numbers, they have 1 minus those numbers. And so along the top, You could have 0.10 right here. You could have 0.05 right here, and you'd have 0.025 right here. They mean exactly the same thing. The columns mean the same thing. They're just telling you how much is in the tail instead of how much is all the way over until you hit that tail.
What words do you think would like indicate that we have to add the 2.5? Or like, is there a problem where like, we don't have to add 2.5 to the confidence interval?
For the confidence interval one, it's truly going to depend on your table. So if you have a question on whether or not you're doing it correctly, you'll want to show me what table you're using.
Oh, I just meant like, you know how you're adding the 95% to the 2.5 to get like 97.5?
Yep, whenever you're doing this type of problem with the confidence intervals, you're going to add them. Yep. Unless you have the other table where it's 0.025 and then you don't have to add it. You'll just need to know that there's 2.5% left in this tail over here. So you'd be looking for 0.025 if that's the class you're in and the table that you're using. Yes.
But anytime you're doing like the t-values and stuff like that, that's what you plug in like whatever you find for the degrees of freedom into this instead of like the 1.96.
Correct.
Okay.
Yes. So if we're on the T table, we can't use the 3 numbers that I gave you. Those were Z scores, not T scores. Yep. Good question. So yeah, in an earlier class, I gave you 3 Z scores, and I said if it's a 95% confidence interval, you're always going to use 1.96. That's because it was a Z, not a T. We can't do that when it's the T. So anytime it's a small sample size and we end up on the T, you can't use my numbers. Sorry. If it's the Z is the one where we can just memorize them. I know this stuff's a little tricky. The best way to figure it out is to do the homework problems and then to figure out how your own table is working for you so that you understand where your columns are, because I know I have to switch back and forth on what I call things depending on which class you're in. Okay. So I've got the confidence interval. The next question said, give a practical interpretation of the interval. What they're asking there is, what does that mean, Jen? And so because this is a 95% confidence interval, this means I am 95% confident that the true mean skidding distance for the population is between 311.6 meters is the unit that we're using in this problem, and 435.9 meters. So I'm not 100% sure that this is where the skidding distance is going to be, but I'm 95% sure that the true mean skidding distance is between those two numbers. 95% sure is pretty sure, but I still got 5%, not 100%. The next question that popped up for that homework problem is a little, I don't like it, but I'll explain it. It says, what conditions are required for the inference to be valid? Are these conditions satisfied? When we're using a small sample t-test to do a confidence interval here, we have 2 conditions that we're always going to be assuming. One condition So condition 1 is that this is coming from a random sample. Now, the good news is in this problem, it actually says that these things were measured at randomly selected road sites. So it is random. So that one I can go ahead and say, check, we've met that condition. Condition 1 is satisfied. Okay. Condition 2. Because this is a small sample and I'm having to use the t-test, I'm assuming that this is coming from a distribution of a population that's approximately normal. So I'm assuming that the population distribution is approximately normal. Okay. This one's harder for me to say, are we meeting this condition for sure or not? Because it's, when we say approximately normal, that's kind of up to the researcher to determine if we think it's approximately normal or not. And so we can make a mistake when we do this part. To know if it's approximately normal means that it would be approximately our bell-shaped curve. And if we were to take all the different values that they gave us, the 16 values that were up here, a lot of them were in the 400 range and a lot of them were in the 300 range and the 200 range. If we made a histogram for that, so here's where the 200s are, here's where the 300s are, here's where the 400s are, this is what it looks like. And so is it approximately normal? Sure. Like, it's not great. So honestly, I look at that and I go, it has an appearance of trying to be normal. Is this normal enough? Is usually where we land on, like, is it looks approximately normal. Is it normal enough for me to say that this is approximately normal? And the answer is, there's not a good answer for that. So have we met this condition? Well, I'm going to assume that since this is a homework question and they asked you to do this homework question, I'm going to assume that they said yes, that it was approximately normal, and we'll check it off. But in actual situations, when you're the researcher and you have to determine if this is approximately normal, like, you're going to say yes or no based on whether or not you think it's close enough to a normal distribution. You might decide, no, it's not, and so I can't use this test. But we don't have any other tests to use at this level in Stats 13. So we're going to go with yes, because you don't, if we say no, then I don't have a test for you. You can't do this problem otherwise. So we're going to go with yes, it is. And then if someone wanted to argue with your results, you could say, yeah, you make a valid point because that's not exactly a normal distribution. Is it approximately normal? And go, I determined that it was. And so that was why I went ahead and used this test. And so we actually do that a lot when you're doing real research stuff. You'll put in that you went ahead and did a particular test, and then in your research paper, you have to say, you know, you'll post that graph and you'll say, I decided this was approximately normal. And then you're being honest with your people who are reading your paper. And then if they decide, yeah, but I disagree with her results because I don't think that's approximately normal. That's how research, and that's how, like, the scientific community, like, has discourse about these types of things. So someone could disagree and then they'd say that's not a valid test. And if you were really into stats, you'd have other tests you could go do now, but we don't have any other tests. So it's the only one we can do in Stats 13 if we got a small sample. So we're going to say yes. Okay. This next question, I hope is not hard. It says, a logger working on the road claims that the mean skidding distance is at least 450 meters. Okay. Do you agree or disagree? Here's what you said. Do you agree or disagree with him? You disagree with him. Why do you disagree with him? You're saying that you're 95% sure that the skidding distance is between 311.6 meters and 435.9 meters. And this dude's saying it's at least 450 meters. He's probably an exaggerator. He's out there logging all the time and he's like, it's at least this much. And you're like, oh, that's not what my data shows. So you disagree with him because you're 95% sure it's between these numbers. Is it possible it's 450 meters? Yeah, because you're still 5%. It could be something else. But 450 is pretty far past your end number there. So that would be pretty crazy that he's like, it's at least 450 meters. That would mean your data is really wrong. So you disagree with him because you're 95% confident. The mean is between 311.6 meters and 35.9 meters. That's why. So when you go through this homework question, this one, the one that was the example that it was walking you through, it was using 95% confidence interval. It's possible they gave you the same thing, but they changed up what the confidence interval was. If that's the case, you'll have to change your T. The other parts will all be the same, but you have to change the T. If they change the numbers on you entirely, then you'll have very different numbers. But you can Google mean and standard deviation calculator, type in the list of numbers, and it'll do that calculation for you. For homework stuff, that's not cheating, because in the real world of statistics, no one's asking you to do this with a calculator by hand. It's not how that works. You'll be doing it in a statistical program, and you'll be entering your data, like you'll upload an Excel file. You'll never even type these things in that way, probably. Someone will hand you a data file, you'll put it in, and you press a button and it runs all that stuff for you. So mostly what you're doing in this class is learning what is these, like what each of those words mean. To actually be able to calculate the stuff by hand, you're doing it for some homework questions, but in the real world, that's not how it would ever happen. So that's why it's funny when people be like, didn't you like do statistical analysis for a research paper? Uh-huh. And we used R for it, and I literally never calculated standard deviations or any of that by hand. I just put the data in and I hit a button and it did it for me. And then you do all of the interpretation of it. So it's important for you to understand what it means when you get this to pop out. Like you'll be able to put the stuff in, it'll tell you what the confidence interval is, but you have to understand this part. I'm 95% confident that my true mean then falls between those numbers. It's important you understand what it means when you get those numbers. Getting the numbers, less important. Okay. So that was a requested question. This one, no one wanted. But Jen should go over an example of it because it's one of our matched pairs. So we already did means where they were independent samples. These ones are not independent. And so we have two different samples here. We have a mean score before class and we have a mean score after class, but they're matched because this person has two scores. They're matched to that person. These are two scores for that same person, two scores for that same person. So often when you're going to be doing the matched sample t-test, it's going to be the same person or the same subject or the same something that has like a pre-test and a post-test, or a before and an after is usually how these work. So the words say, a golf instructor is interested in determining if her new technique for improving players' golf scores is effective. She takes 4 new students and she records their 18-hole scores before the learning technique and then after they've taken her class. So they have a before score and an after score. She conducts a hypothesis test and the data are as follows. And the actual question for the homework, so this was in the OpenStax textbook. This was one of the homework questions. Literally, it was like, the correct decision when she does this hypothesis test is it to reject the null hypothesis or to not reject the null hypothesis is the whole question. And it doesn't have you go through any of the other steps in between. But in order for you to actually honestly answer this question, you have a lot of work to do, but it seems like such a simple question because it's like, do you reject it or do you not reject it? And you're like, well, they're not showing all the background behind what you would be doing to make that decision. So we're going to go through those steps. I went ahead and put down the steps we're going to need to do that. We're going to need to calculate a t-score here. And this is a different formula than the one that we used when they were independent samples t-tests. So you have different formulas depending on which test we're doing. If it's matched, then this is the one we're going to use. And as part of that formula, I know it's super tiny, but in there you have the standard deviation with a little d underneath it. That means you're finding the standard deviation for the differences between these scores up here. And so that's this formula right here. So multiple formulas we're going to have to use in order to answer this question. I'm very happy we have a tiny sample size because otherwise this becomes a beast of a problem to do. But with only 4 people with 2 scores each, becomes much more doable. Okay. So in order to do the test statistic, our t-score here, and it's definitely a t-score with only 4 people, we need to know what each of those variables in there stand for. The x bar sub d is the mean of the sample differences. The mean of the sample differences. So when I calculate a difference here, this minus this, or this minus this, I'm going to get sometimes a positive number and sometimes a negative number. So it matters how I calculate that sample difference. So I'm going to put difference down below this table here. And I'm going to ask you what would make sense for a difference. You took a score before the person had a class, and then you had a score after the person had a class. And in terms of us doing 18 whole scores, if you understand golf, do we want higher scores or lower scores in golf? Yeah, so like when you get a hole in one, meaning that like you only had to do 1 stroke, you're happy about that. If it takes you 5 strokes to get that, we're not happy about that. Having a higher score is bad in golf. So the fact that player 1 had a score of 83 before and an 80 after is not bad. Like if you were doing like a math test, we'd be sad. We'd go, oh, they got a lower score after they took the class, but this is good. However, player 2 had a 78 before and got an 80 after. So player 2 actually got worse. Player 3, though, got way better. And player 4 got a little better, right? So when we go to do the difference between these, usually what we do is we take the after score and we subtract the beginning score. Okay, so if I take the after score and I subtract the beginning score, are you cool with me getting a -3 there? My after minus my beginning, I actually get a +2 on this one. That's bad. 86 minus 93. I don't even need you to be able to do that in your head. 86 minus 93 is going to be a -7. Okay, but we should probably be able to do the other one in our head. 86 minus 87 would be -1. Those are my differences. Okay. So if I want my mean difference for these things, my mean, whenever we do mean, that's our x bar, right? I'm going to do x bar with the little d after it to say what I'm doing is taking the mean of these 4 numbers, the differences we just calculated. So we're going to take -3 and we're going to add 2 and we're going to add -7 and we're going to add -1. And there were 4 numbers there, so we're going to divide by 4. That's us calculating the mean difference. So I got -2.25. The standard deviation part is a way bigger calculation over here. And I need it in order to do the test statistic part, because that standard deviation is this one little part of this big formula here. So I need this calculation. So I'm taking the square root of, okay, and here's what's happening. The D here is the difference for each pair. So that would be a D, this would be a D, this would be a D, this would be a D. And we're subtracting the X bar that we just got. If we're subtracting a negative number, you're actually adding them. Is that okay? So I'm going to put the first one in there is -3. And I'm subtracting a negative 2.25. So I'm going to turn it into a plus sign and add 2.25. And then I'm supposed to square it. That little sum sign in front says we're going to add up 4 of those things. So now I'm going to take the next number, the positive 2. I'm subtracting a negative 2.25, so it's plus 2.25. And then we're going to square it. Then I'm going to take the -7. I'm subtracting a negative 2.25, so we're going to add 2.25 and square it. And then we got one more pair, -1. We're subtracting a negative 2.25, so we'll add it and square it. And then that whole thing is getting divided by n-1. Our n, we have 4 pairs, so this is going to be 3 down at the bottom. Okay. Should this number come out to be positive or negative? Has to be positive. Why does it have to be positive? Well, one is underneath the square root sign, so if we get a negative under a square root, we have a problem. So it better be positive. But another reason is, even though we might get some negative numbers inside parentheses here, because we're squaring that thing, all of them are going to pop out a positive number for us. So once we actually do this calculation, I already did it, we get approximately 3.77492. So now I'm going to come back up to my actual test statistic, which is what I need. All of this was so that I'm going to be able to go do my test statistic. So test statistic, I'm supposed to take the X bar sub D. We got that number there. That's our negative 2.25. And then we're supposed to subtract the mean difference for the population. Just like we talked about on Monday with those formulas, this always ends up being a 0 when we're doing these problems. We're going to divide that by the S sub D we just got, so the 3.77492 divided by the square root of our n, and the n was 4 for this one. So this comes out to be approximately negative 1.19. If this had come out to be a positive 1.19, what I'm about to do doesn't change. So it doesn't really matter if we get a positive or a negative on our T score. I need my T table because this is a T score. Okay. What are my degrees of freedom for this problem? How many pairs of things did we have? 1, 2, 3, 4 pairs. So my degrees of freedom for this problem is 4 minus 1. So that matters when we do these ones. When we're doing the matched we actually care about the pairs because we're caring about how many differences are there, and we had 4 differences. So degrees of freedom is going to be 3. All right. Normally, when I pull up this table, what we're doing is we're looking for a certain level of confidence or a certain level for our test. And then we look down here for the degrees of freedom. And that will give us the t value that's in here. But we just got a t value. So I don't need the t value. I have the t value of negative 1.19, but I said I don't care if it's positive or negative. So we're going to say positive 1.19 because nothing on my table in the middle has negative numbers. So I want positive 1.19. And I want to look under degrees of freedom 3. So here's degrees of freedom 3. 1.19 is closest to this number right here, right? So that means that it's between some number that's hanging off the table. So instead of 0.95, if we're going this way, it'd be like 0.85. It's going this direction. So if the number that I got was between these 2 numbers, then I would be talking about something between a 95% confidence interval and a 90% confidence interval if it fell between 2.353 and 3.182. But our number is actually off the table over this way. So what that means is we don't even have a 90% confidence interval. We're in the like 80s or the 70s range. So we're not particularly confident. This one, we're doing a hypothesis test. And it didn't tell us when we did the hypothesis test, when I read the question, it didn't say alpha is 0.05. It didn't say alpha is 0.10. What did your instructor say to assume if it doesn't tell you? Or did they not? Rule of thumb is, since they didn't say, they didn't give us alpha, we assume alpha is 0.05. That's just an assumption that we make if they don't say. So that's the same as like the 95% confidence level alpha. That's usually the standard. They didn't tell us, so we're going to assume 0.05. So when we did the one with the t table before, and we were looking up here, and I said if it fell between this one and this one, then I knew it was between a 90% confidence interval and a 95% confidence interval, but we're actually like off the table over here. So that means that our alpha is actually going to be somewhere, if it's, let's see, this one would be, if that one's our 90%, then this one would mean we had 10 on each side. So this would be a 20%. So our value in terms of what our p value that we're looking for, our p, we said that this one would have been a 0.05. This one would have been a 0.10. We know that our p value is going to be bigger than the 0.10. So because we're over here and I already forgot the number, 1.19 is off my table, that means that my p value is definitely bigger than the 0.05. So because the p value is definitely bigger, and I know it's actually bigger than 0.20. And the reason I know it's bigger than 0.20 is that if it happened to actually be exactly 1.638, which it isn't, that would mean that we had 10% on each side, and we always multiply by 2 for a two-tail test. So because we have at least 10%, I know this is bigger than 0.20. So 0.20 is bigger than our 0.05. We fail to reject the null hypothesis. So when it was asking the question, should we reject it or not reject it? The answer is B. We do not reject the null hypothesis because our p-value was not smaller than 0.05. Our p-value was at least 0.20. If you have something that will let you actually calculate the p-value, so like I took our t 1.19 and I put in our 3 degrees of freedom into one of the online calculators, the actual p-value from the computer was 0.3196. So we're not lying, it's definitely bigger than 0.05, but we didn't actually need to have like the computer tell us the exact one. The table was enough to tell us we were too big. But if you really wanted to have the answer, as researchers, you would have a computer program that would tell you what the actual p-value was, and it'd be way easier to say, yeah, reject that. Good work, guys.